Rolling thresholds can miss a small persistent shift until CUSUM shows the accumulated evidence. You'll run a two-sided CUSUM to flag the first sustained upward mean shift before any pointwise alert. I'm Professor Pi, teaching AI foundations with simple Python. A sensor can stay within its usual limits while quietly drifting away from normal. That matters in manufacturing, health monitoring, and model quality checks. A single bad reading is easy to spot. A long run of slightly biased readings is harder. CUSUM solves that gap. It collects small pieces of evidence over time, then signals when the total becomes convincing. We will use residuals, which are the differences between observed values and expected values. We will build from a simple missed alert to a detector that catches the same quiet upward movement. The key idea is simple. Normal noise should cancel out, while a real shift should keep adding pressure in one direction. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Let's start by seeing why a fixed pointwise rule misses this stream. This snippet creates a small NumPy residual stream where no single reading looks alarming. The early values hover around 0, then the later values settle slightly higher. That is exactly the pattern a pointwise check can miss. np.abs measures each residual on its own, and np.flatnonzero finds positions beyond the fixed threshold of 2.0. The largest absolute residual is still below that line, so the pointwise rule produces no alert. The printed result shows the blind spot clearly. Nothing looks extreme in isolation, yet the later readings are no longer behaving like the earlier ones. A missed pointwise alert is useful evidence, but we still need a way to reveal the drift building over time. This example uses np.cumsum, which calculates a running total, to show why persistence matters. Instead of judging one residual at a time, run carries the accumulated total through the stream. When the shifted values arrive, their small positive contributions begin stacking up. Then cross finds the first index where that total passes 3.0. This is not yet a proper detector, because normal negative variation cannot clear out old positive evidence. Still, it exposes the core signal. The output shows the first accumulated drift step, showing why repeated modest values can matter more than one unusually large value. A running total can also remember harmless noise for too long, so the next version needs a way to forgive normal variation. This code turns simple accumulation into a two-sided CUSUM detector, with separate positive and negative state. Pos grows when residuals repeatedly exceed the reference value k, while neg tracks sustained movement in the opposite direction. The max and min resets matter because they clear evidence once noise pulls back toward normal. That prevents old harmless wiggles from building forever. When either score reaches the decision limit h, the detector records an alert. Increasing h usually delays alerts and reduces sensitivity. Decreasing it catches shifts sooner, but can create noisier alerts. The output shows the first upward CUSUM alert and the score that crossed the limit. For more practical Python and data science lessons, you can subscribe and keep building these habits step by step. The detector works now, but its reference value controls what counts as meaningful upward movement. This snippet compares several k choices instead of treating the reference value as magic. First up keeps the same upward CUSUM logic, but returns only the first upward alert step. That makes the candidate settings easy to compare. A smaller k counts more of each positive residual as evidence, so it tends to fire earlier on this stream. A larger k discounts modest movement. That can help when normal residuals naturally wiggle more. np.argmin selects the candidate with the earliest non-missing alert. The output shows which tested k is most sensitive for these residuals, giving you a direct way to connect tuning with detection behavior. Choosing K is only half the practical job. We also want a compact function that can inspect a stream and stop as soon as a shift appears. This example packages the detector into CUSUM alert, a small streaming baseline you can call on sensor residuals. Each new X updates pos and neg, then returns immediately when either side crosses H. The same residuals are also checked with np.flatnonzero and np.abs to keep the comparison honest. The pointwise rule still sees no extreme observation. In a project, these residuals could come from a calibrated sensor model, where remaining errors should usually center near zero. The output shows CUSUM finding a sustained upward shift before any pointwise alert fires, which is the practical advantage we wanted from the beginning. When the normal baseline itself changes often, a fixed CUSUM setup needs care. A seasonal pattern, a changed production batch, or a recalibrated model can look like a mean shift. In those cases, update the expected baseline thoughtfully and review alerts against real events instead of treating every crossing as proof of failure. This example shows why CUSUM is strong for small, persistent changes. Pointwise thresholds are better when you need to catch sudden spikes. CUSUM is better when the risk is a quiet drift that keeps moving in one direction. Try changing K and watch how the first upward alert moves. Then adjust H and compare earlier detection against extra sensitivity to noise. What practical monitoring topic would you like to explore next? Leave a comment and subscribe for more clear Python and AI foundations.